So here's my question for the student. And the question's pretty simple, but it's where we left off. So here's our question. Does baseball talent fall into a normal distribution? Remember a normal distribution. Here we'll do another freehand of it. Bell-shaped curve. And if I were measuring talent, remember this is the mean, the median, and the mode on a bell-shaped curve. And when I measure any form of baseball talent, even using various outcome measures that I hope represent talent, is it going to follow a normal distribution? Let's just do a study. Let's try to measure something to see if baseball talent falls into a normal distribution. And our surrogate for baseball talent is going to be OPS. OPS as a measure of hitting talent. That's our measure of talent for this little study, OPS. And we're going to see if OPS as a measure of baseball talent falls into the normal distribution. So we're going to run a SQL query. I'm going to go to the sandbox and show you my query. I'm going to then switch over to RStudio and do a histogram. So here's my SQL query entered into the SQL sandbox. And you can see what we've done here. The query is pretty straightforward. What we're doing is putting in the player ID, year ID, team ID. We're calculating plate appearances, on-base percentage, slugging, and OPS. And these are the formulas that we've been using for each of those statistics. We're taking it from the batting table. We're just using the year 2013. Plate appearances greater than 299, 300 or greater, and we're just going to order by OPS descending. So let's run this query, and here are the results for 2013. Top player Miguel Cabrera, his OPS was 1,078, and we have 270 rows. Now this is pretty good because there are 30 teams in baseball, so 270 divided by 30 equals 9. That means we have 9 players represented here in our database for each of the teams. That's on average, so that's actually pretty close to what I'm thinking about in terms of replacement level, full-time versus replacement level. But I like 270, so that choice of 299 plate appearances, which we had at the top here, that choice of 299 plate appearances looks pretty good. Now, what I've done is create this little data set, and I'm going to download the results. We'll have this query for you so you can run it yourself, but it's pretty straightforward. You've done this before, and you might want to start saving your SQL queries in some special place in a text file for this course so you can go back to them as needed. But I was just downloading full results, and then we'll go into RStudio and look at code that can generate a histogram of these data. So now we're back in RStudio, and let's plot a histogram of the data we collected in the SQL sandbox. There's a command here that we should be familiar with, the function read CSV. It's going to read a file name Layman Sandbox 7, and that's what was saved from the SQL Sandbox earlier. So I'm going to run this. Down here, it looks like it ran fine. Let's check in the environment, the global environment. Here is the data frame OPS_2013. That's the data frame that was created with the run CSV function. 270 observations, just like we found in the SQL Sandbox. If I click on it, yes, it looks like the same spreadsheet, the same data frame that we had before. Miguel Cabrera at the top with a 1078 OPS. So that looks good. And now we're going to come down here and try to understand the next command. The next command is a qplot command. And remember, we can always go to help and find out more about qplot. Qplot is quick plot, and it's part of the ggplot package. Now, I've installed the ggplot package. So let's run it. It's going to do a histogram of the OPS data column inside the OPS underscore 2013 data frame. It's going to take that one column and do a histogram. And that's what this command says. If it's one variable, it can do a histogram. The bin width on the histogram is set with another parameter to the function. And I also can outline the bars in the histogram with a certain color. Let's run this function. qplot, oh, there it is. And here's our output. Now this output doesn't look normal. It looks like it's skewed to the right. And this is what Bill James was talking about when he talked about how using average was probably incorrect. You needed to start thinking about replacement level, which is somewhere down here at the other end. Let's transfer this plot to my PowerPoint deck, and we'll analyze some of the data associated with OPS in 2013 to think about its nature as either being normal, a bell-shaped curve, or potentially skewed. And we used R to help generate this graph, and we'll take a closer look at this graph now. So this is the histogram of the OPS data from 2013 of all batters who had at least 300 plate appearances, OPS 2013. And this data set runs from the lowest OPS in that group of 0.548, 548 OPS, which is very low, to Miguel Cabrera's, which is 1.078 OPS. Now the first quartile is 0.6807, and the way this works is it's right about here. Here's the first quartile, somewhere right in here. This is the first quartile. The third quartile for this data set is 0.799. So that's right about here. This is the third quartile, right about here. Third quartile. As you can see, most of the data is right here. 50% of the data is right through here. And what that tells you is there's a real distribution of data above an OPS of 800. That's 1/4 of the data set. Okay? And it really does fan out like it's skewed. The mean is 0.742 OPS. The median is 0.736. So the median is less than the mean. The median is over here. This is 0.7. This is 0.7 right here. So 0.736 is somewhere in here. This is the median. The median is right about here. And the mean isn't too far. The mean is greater than the median, meaning there is likely a skewed distribution, pulling the mean away from the median. If it was normal, it would be equal. These two values would be equal. So remember, n equals 270 here. There's 270 players who met our criteria of OPS that we studied in 2013. And this is what the data look like. And it just looks like there's a lot more data near the 25 percentile mark. And the data from the third quarter on, the last quartile, is much more spread out in a distribution. And here's what to think about this. This really looks like a very nice rising distribution. And this area here looks like it might be something like replacement level. So, again, let's just think about the normal population. There's a normal curve. If we're measuring something, that's a bad curve, but just go with it. There's a normal curve, and if we blow up this section right here, the extraordinarily high away from the mean section, let's draw that. that section is going to look like this. If I just take this section right here and blow it up, you know, this is the end of the bell curve. The end of the bell curve is going to have a shape kind of like our curve here. That's what the end of the bell curve is going to be like. And this is what Keith Woolner writes about in Baseball Prospectus Annual 2002. So I'm going to say BP Annual is where Keith Woolner describes replacement level. If you can find this, or you can find this book in the library, well, this is where Keith Woolner lays out his argument for VORP. VORP is a creation of Keith Woolner. It's a batting-only creation. It's really been superseded by various warps or wars that are out there now. But the start of this whole idea of really looking at replacement level with some good analytics was VORP by Baseball Prospectus and Keith Woolner. So Keith lays out his argument for his choice of replacement level with his article in the BP Annual in 2002.